Hi, everybody. Here we are with another video solution. Section 5.2, exercise 2D, which says the following. For the matrix A, I've typed it out in sort of a row form, but it's also written here. A is the matrix 7, minus 4, 0, 8, minus 5, 0, and then 6, minus 6, 3. It's a matrix over R, so the base field is real numbers. The instructions are to test A for diagonalizability, and if it is in fact a diagonalizable matrix, then find an invertible matrix Q and a diagonal matrix D, so that Q inverse AQ is equal to the diagonal matrix D. All right, so here's our matrix A, and in order to test for diagonalizability, we need to first figure out the characteristic polynomial, determine whether or not it splits. And if it doesn't split, then we're done. We already know that A is not diagonalizable. If it does split, then we need to look at the multiplicities of each of the associated eigenvalues and determine whether or not those match the dimensions of the associated eigenspaces. So let's begin. Let's calculate the characteristic polynomial of A. That will be the determinant of the matrix A minus T times the identity, in this case, the 3 by 3 identity. So let's write down what that matrix is. Well, A minus T times the identity, that's only going to affect the diagonal entries. So we'll get a 7 minus T, but then a minus 4 and a 0 unchanged. The next row will be an 8 minus 5 minus T, and then a 0 again. And the final row will be a 6 unchanged, minus 6 unchanged, and a 3 minus T. All right, so there's the matrix we now need to find the determinant of. And my instinct says to use the last column since there are a bunch of zeros. So we'll do cofactor expansion along the last column. We'll find 0 times a 2 by 2 determinant, doesn't matter. Minus 0 times the 2 by 2 determinant, doesn't matter, plus 3 minus T times the resulting 2 by 2 determinant of the minor, which is just 7 minus T times minus 5 minus T, minus 8 times minus 4 would be negative 32. So I'll turn that into a plus 32, and that's it. That's the determinant. Well, we can't exactly determine whether or not this polynomial splits here because of that plus, adding 32 to an otherwise product of monomials. So we're going to have to expand this out. We'll leave the 3 minus T alone because that actually is a factor at the moment. And inside these square brackets, let's see, we'll get a negative 35. Minus T times minus 5 is positive 5T. 7 times minus T is a minus 7T, so that will net us a minus 2T. And finally, we'll get a plus T squared. Let us not forget our positive 32. Okay, that should simplify nicely. We'll get a 3 minus T times, I'll write this as T squared, minus 2T, minus 35 plus 32 should be minus 3. Oh, that's great. That's a polynomial that factors. So let's go ahead and factor that into T minus 3 and T plus 1. Let's double check we did that right. I get minus 3 and plus 1 is a minus 2. Good. So I will rewrite this now in sort of my preferred form for the polynomial. I want this 3 minus T and the T minus 3 to match. So I'll write it as minus 1 times T minus 3 squared times T plus 1. So what does this tell us? This tells us that there are 2 eigenvalues. One is 3 and one is negative 1. The eigenvalue 3 has multiplicity 2. The eigenvalue negative 1 has multiplicity 1. And in fact, the characteristic polynomial splits. So there is at least hope that this matrix A is in fact diagonalizable. Let's observe that the eigenvalue associated to, or the eigenvalue negative 1 must have at least one eigenvector So there, the eigenspace dimension will definitely match the multiplicity of the eigenvalue. So the only thing that will really determine now whether or not A is a diagonalizable matrix is whether the eigenspace for eigenvalue 3 has dimension 2. So let's investigate that. Let's look at the eigenspace associated to the eigenvalue 3. And it can either have dimension 1 or 2. If it has dimension 1, then 1 does not match the multiplicity 2, and A will not be diagonalizable. But if the dimension is 2, then all of the eigenspace dimensions will match the multiplicities of the associated eigenvalues, and A will be diagonalizable. All right, so eigenspace associated to 3, that's the null space of A minus 3 times the identity. We sub in the actual value for lambda there, lambda equals 3. So let's go back to our original matrix. A is that. I'm going to subtract 3 times the identity. So that should leave us with a 4 in the first entry. And then minus 5 minus 3 will be minus 8 in the middle entry. And 3 minus 3 will be a 0 in the last entry. Right, so we want to find the null space of this 3 by 3 matrix now. And I'm going to quickly and maybe verbally do a few of these elementary row operations. The first row we could divide by 4, and we'll get 1, minus 1, 0. And hopefully it's not too hard to see that you could do the appropriate multiplying of that first row by a constant, adding to the second and third rows, and completely eliminate the second and third rows, turning them all into zeros by standard Gaussian elimination methods, elementary row operations. All right, so this null space then, let me write it in full form. Well, this is going to correspond to, if we wanted to call the variables x, y, and z, this will correspond to the equation x minus y equals 0, and there will be no restrictions on z. So the standard thing to do is to assign to z a free variable, and then the y will also get a free variable, call it s, and then the condition that x minus y equals 0 will have to mean that x equals whatever value we assign to y. So the entire null space is the set of all vectors of the form SST, where S and T can be any real numbers. Well, let's observe quickly that this has got to be a two-dimensional space, since there are 2 free parameters. So this is two-dimensional, matching the dimension, the multiplicity of 3 in the characteristic polynomial f of t. So this alone now tells us that A is going to be diagonalizable, since, as we said, we already know that the eigenspace associated to eigenvalue -1 will be one-dimensional, since there must be at least one eigenvector, and the dimension of the eigenspace is always less than or equal to the multiplicity of the eigenvalue. All right, but that tells us that A is diagonalizable. It doesn't tell us what the invertible matrix Q and the diagonal matrix D doesn't tell us what those are. So in order to do that, we have to actually find do the rest of the work and find associated eigenvectors and build a basis and so forth. So knowing that this null space is the set of all vectors of the form SST, where S and T can be any real numbers, let's write down a basis for the eigenspace associated with 3 is, all right, well, S could be 1 and T could be 0, or S could be 0 and T could be 1, and those are nice vectors. You can check, in fact, that these are certainly linearly independent and you could check easily that they are in fact eigenvectors for the matrix A with eigenvalue 3. Next, let's look at the eigenspace associated with the other eigenvalue, which is -1. We already know that there's going to be at least one eigenvector, but we need to actually compute the null space of the matrix A minus -1 times the identity in order to find that eigenvector or some eigenvectors. So let's see, that's going to be the null space of A plus the identity, -1 times the identity, just adding the identity. So that'll add 1 to each of the diagonal entries. So I'll have an 8 minus 4 and 0. 8 minus 4, 0. Second row will be 8 minus 4, 0. Oh, that looks good. And the last row will be 6 minus 6, 4. All right, so these computations are going to get a little bit trickier, I suppose. Let me quickly move this out of the way so that I have a little bit more space to work with. There. All right, so let's do a little bit of quick elimination. Certainly we could take the first row and divide by 4, leaving us with a 2, a -1, and a 0. We could use that row to eliminate the second row, and for niceness of reduced echelon form, let's move that to the third position. And then what was the third row will become the second row, and let's go ahead and divide each of those terms by 2 as well, so that we will get 3 minus 3, 2. All right, that's one step, but certainly doesn't finish the job of reduction. I don't really need ones, and I don't want to deal with fractions if I can avoid them. So I'll leave the first row as 2 minus 1, 0. But then that means that in order to eliminate the first 3 in the second row, I'll have to do something like multiply the first row by -3 halves and add it to the second row. So what that will do is leave us with a 0 in the first entry, and then -3 halves times -1. Let me actually write some of this out. So -3 halves times -1 plus -3. And that will be +3 halves minus, I'll call it 6 halves, leaving us with -3 halves. And then times 0 plus 2 will leave us with a 2 there. All right, so there's a little bit of scratch work there. You can check my calculation. And all right, let's go ahead and clean that up just a little bit. I'll call this the null space of 2 minus 1, 0, 0, minus 3, 4, 0, 0, 0. And again, that's not actually in reduced echelon form or even row echelon form, but it'll be enough to be able to write down a nice basis for the eigenspace. So let's just see what these look like. I guess we can see pretty quickly that there is only going to be one free variable. I'll let the z component be that free variable. So if z were t, then the second row of the matrix would mean that -3y plus 4t has to equal 0. So that should give me 4/3 t as y. And then the top row will be 2x minus 1 times y, which is 4/3 t. That has to be equal 0. And let's see, 2. I think that will give us 2/3 t. So this is just solving the system of equations. I'm doing it fairly quickly in my head, but you could write this down more carefully or work it out with more detail if you'd like. So I claim that the null space is equal to all vectors of this form, 2/3 t, 4/3 t, t. but t can be any real number. So let's observe that this should be exactly the same as if we were, actually, let's not even rewrite it that way. Let's just observe then that this is a one-dimensional space and say that a basis for E minus 1 is, well, I could let t be 3, and then we would have nice eliminations of the fractions. So I have 2, 4, 3 as my basis for that eigenspace. Again, you could actually take that vector now, multiply it by the matrix A, and check that you actually end up with -1 times this vector 2, 4, 3 to verify that yes, in fact, this is an eigenvector. And since the eigenspace is one-dimensional, every eigenvector will just be a scalar multiple of that one eigenvector. Great. So now we have bases for each of the respective eigenspaces. We know that the dimensions of each of the eigenspaces matches the multiplicities of each of the eigenvalues in the characteristic polynomial. So all that remains from the instructions is to find the invertible matrix Q and a diagonal matrix D. So the Q inverse A, Q is equal to D. So the way that we're going to do this is to let Q, the columns of Q will be the eigenvectors in the bases we have found, and the entries of D will be the associated eigenvalues in the appropriate order. In other words, here's what we can do for Q. What we've really done is by finding a 2-element basis for E3 and a 1-element basis for E minus 1, we can put these 3 vectors together to get a basis for R3 consisting of eigenvectors. So let me just take each of these 3 vectors and write them one by one as the columns of Q. So I'm going to take the 2 vectors from E3 first, 0, 0, 1, and then the vector from E minus 1. That will be 2, 4, 3. So in particular, the first column had a corresponding eigenvalue 3. The second column had corresponding eigenvalue 3. And the third column had corresponding eigenvalue -1. So then the diagonal matrix will have those eigenvalues in that order. And if we had chosen to write Q with those columns in a different order, we would just have to write D in the appropriate order so that the first eigenvalue, the first diagonal entry, matched the eigenvalue of the first column of Q, and so on and so forth. Let's go ahead and fill this diagonal matrix out with zeros, since it should have only non-zero entries on the diagonals. And if you want to confirm that this in fact works out, well, what we're told is that we need to check that Q inverse AQ is equal to D, but observe that this is true if and only if AQ is equal to QD. So without even having to compute the inverse of this Q matrix, we could just take the original matrix A and multiply it by Q, A on the left, Q on the right, and then take these 2 matrices, Q and D, multiply them together with Q on the left, D on the right, and in fact, you will find that yes, these do result in the same 3x3 matrix. All right, guys, thanks so much. Hopefully that was helpful. If you have any more questions or any other exercises you'd like to see, please let me know on the forum.